Let's start solving today's lead code daily challenge question, which is 1557 minimum number of vertices to reach all nodes. So let's try to understand the question first. So given a directed acyclic graph, okay, so this is the observation. Acyclic graph is given to us with n vertices numbered from 0 to n minus 1, okay. So 0 indexed vertices are given to us and an array edges which is representing a directed edge from node A to node B, okay. Then finally we need to find the smallest set of vertices from which all nodes in the given graph are reachable, okay. So what this particular question is asking from us, like we need to return a set of vertices from which we can traverse the whole graph. So minimum number of vertices we need to return from which we can traverse the whole graph. Okay, so let's try to understand this particular question with an example first. So let's suppose this is a graph given to us, and let's try to see what are the smallest number of vertices required. So 0, okay, because 0 is not reachable from any another node, so I need 0. But do I need 1? So this particular vertex is not required because 1 can reach from 0th vertex, same as well as 2, because 2 can reachable from 0, as well as 4, as well as 5 we can reach from 2. Now what about 4? Can we reach 4 via some another node? Yes, 3. So 3 I need to add in my particular answer, and 4 no need to add 4 because 4 can be reachable by the third vertex. So this will be my answer of this particular example. Now let's try to build an intuition how we can intuit this particular approach, okay. So let's try to see another example to clear the intuition we are going in the right direction or not. So in this particular example, so the question is, do I need to add particular B vertex into my final set or not? Into my final set. So if this particular question is clear, we will get a very helpful intuition from this example and we can solve this particular question. So the answer of this particular question is no, we do not have to include the B vertex into our final set, because if we include, we can reach B from its using the edge which is coming from A, okay. So similarly we can take the example of D vertex as well. So this vertex we also not able to include in our final set because this particular edge and this particular edge are reachable via their uh, some another nodes or some another vertex as well. In this example it is A and C, so there is no point to adding into our final set. So from this example we got an intuition like, if so we got a very big clarity. So the vertex which are reachable from some another vertices are not able will not be a part of our final set of our answer, okay. So B and C are not a part of our answer, will not be a part of our answer. So from this we got a very big intuition. So the particular approach we are going to use is in degree count. So here we can see B and D vertex have an in degree greater than 0. So here these particular nodes are reachable from another nodes or another vertex, so we are not going to include into our answer. But what about those nodes where in degree is 0? So do we need to add? Now the final question remains, do we need to add those vertex where in degree is 0? So the answer of this particular question is yes, because if the particular vertex having an in degree value is equal to 0, so there is no any another way possible to reach that particular node. So we have to include that particular node into our answer. So let's try to see the intuition which we discussed above, okay. So I will write down the n degree count. So 0 node, what is in degree count? The nodes or the edges are coming to a particular vertex. The number of edges are coming to a particular vertex is known as the in degree value of that particular vertex. So let's take an example of vertex 0. There are no edges coming to this vertex 0. So the in degree count of this particular vertex is 0. Now what about vertex 1? So there is one edge coming to it, so the in degree count is 1. What about 2? There are 2 edges coming to it. Okay, so the in degree count of vertex 2 is 2. Vertex 4, the in degree count of vertex 4 is 1 because there is an edge coming from vertex 3. 5, the in degree count is 1 because there is a vertex, there is a edge coming from vertex 2. Now the same we'll find out for vertex 3. Now the in degree count of vertex 3 is 0 because there is no edge coming to this particular vertex. Now as we seen above, the final answer of this particular question is 0 and 3 only. So if a vertex having in degree count is equal to 0, we will include that particular vertex into our final set. So that's the particular intuition or the particular approach for this particular question. And let me give you a code walkthrough of this, how I solve this. So how we are going to build this intuition into an algorithm. So how we can do it? We can create a boolean array where boolean array represents the same thing. So we can try to convert in degree count to boolean value. So if a vertex is not reachable from any another vertex, so that is a not reachable vertex from any another node, and that we can maintain in our boolean array. So we'll create a boolean reachable array where the reachable array of that particular vertex is going to be true if the in degree count which is greater than 0 of that particular vertex. Okay, so this is the code of the above approach what we discussed. So I created a reachable array where the initial value of the whole array is false, and this is our answer which we are going to return at the end of the algorithm. So required nodes. So I am going to traverse the edges array which is given into the signature of the method. And so what the edges is representing, the each array is representing a edge from A to B. So B is reachable via Ath vertex. So I am going to mark A as true because B is reachable via Ath vertex. So reachable of h dot get 1 is equal to true. And at the end I am traversing all the vertex. If reachable of I is false, so from the above example as we seen, A is not reachable from any another vertex, so A of reachable will be false. Okay, so reachable of that particular vertex is false, and that particular vertex I am adding into my required nodes list, which is our final answer. And at the end I am returning the required nodes. So let me discuss about the time complexity. So here I am traversing the whole edges array, as well as after traversing the edges array, what I am doing, I am traversing all the vertex to check is it reachable or not. So 2 loops I am processing. So the time complexity will be order of E plus V, or you can say order of V plus C, vertex plus edges, and the space complexity will be nothing but order of n only to store the boolean values, all the boolean values for all the vertex. So that's it of this particular question. If this particular video helped you to build the intuition, and from this video if you are able to solve this particular question, like this video and subscribe to my channel. Thank you.